So right now for problem 7, we have our 4 representations of motion that we were trying to solve for worksheet number 5. We have the written description that was provided for us, the motion map that we constructed ourselves, as well as the position time graph, once again constructed by us, and the velocity time graph. However, there is another way that we can represent motion. It's what we ended up doing in the buggy lab. In the buggy lab, we ended up writing those mathematical models to describe motion. That's what I'm going to end up including in my written description right now as our 5th way of representing motion. Our position of object A is equal to the velocity of object A, which is negative 2 meters every second, times the amount of time object A is moving for, plus its starting position of 10 meters. We can represent a mathematical model for object B in the same format. The position of object B is equal to its velocity, positive 3 meters every 1 second, times the amount of time object B is traveling for, plus its starting position of 0 meters. When we have these two mathematical models, we can figure out the position for each of those objects by plugging in the amount of time they'd be traveling for in place of that t variable. If we want to figure out the time that they are at the exact same position, we can end up setting xa equal to xb, which is what I'm going to include in this blank space on the bottom right of the screen. If they are to pass each other, that means that they are at the exact same position. So we set those two equal to each other. Then we just write those equations there. Negative 2 meters per second times time plus 10 meters is equal to positive 3 meters per second times time plus the 0 meters, but I'm going to leave that off just to, well, it doesn't really affect the problem there. So I need to solve for t. So just like in algebra, we need to get that variable by itself. The way that I am going to do that is I am going to add that 2 meters per second times t to both sides. So that way I get my like variables on the same side. The way that's going to end up looking is 10 meters is equal to 5 meters per second times the time. To get time by itself, I'm going to divide both sides by that 5 meters per second, which will then give us a time that is equal to 10 divided by 5, 2. And our units, meters divided by seconds, would cancel out those units into giving us seconds. So the time that they interact at is going to be 2 seconds. If I want to figure out what position that is, I just plug it back into either of those two equations.